Okay, a couple of years ago, I gave a presentation here on how the finance industry uses InfiniBand, and you just heard about from Eurex, one of the biggest exchanges, how they actually make use of InfiniBand. And one of the key characteristics that we require to operate properly is multicast. And so this is kind of a more in-depth view on how multicast works and how we operate with this. This is particularly necessary because we are developing a new thing called LibFabrics, and LibFabrics so far does not support multicast, and so it's right now it's not useful for finance. The traditional IB Verbs API supports multicast, and we've been working for the last 5 to 8 years on various improvements to make it suitable for the financial industry. So this kind of gives you an impression on where we are, what features we rely on, and how we can maybe move forward. So if I press this button, yep. Okay, so how this is going to work is I'm going to give you a short refresher on multicast, because most of you only use unicast if you're not in finance. So I think maybe good to talk about that. Talk about generally why actually we do such strange things. And then the basic rationale in finance, what kind of technology is currently deployed, what is unusual about this, and then some kind of an outlook as to where we would like to see this go and where we have still a lack of functionality. The financial industry is pretty diverse, and so this shows you a couple of these entities. Eurex, that was presented before, is a stock exchange. So they kind of match buy and sell orders, and they are interested in a fair business dealings. And then there's entities that interact with these exchanges, like banks or brokers or companies that I work for, algorithmic trading companies, that try to make good deals and make money off the trades that they do at the exchange. So there's a diverse ecosystem with different requirements, and I'm also going more depth into that one as well. So first of all, what is multicast? So the simple thing is you send a single message to multiple receivers. That is different from unicast, where you only have one receiver, and if you want to send to multiple endpoints, you have to do multiple transactions in order to reach all the endpoints. And this is usually done in hardware. So the routers and the switches that you're using must support multicast. There's protocols there that determine who is in a certain channel and who gets a certain portion of the data. So typically, we have a publisher-subscriber model instead of node addresses. There's certain information on the fabric available, and you subscribe to that channel. And then all the subscribers to that channel get that information, and they ideally get it at the same time. Because the network hardware is doing replication, there's no one-to-one sessions where we would have to go one after another. This is very important for fairness, as was mentioned before during the Eurex presentation. So in some ways, these data diagrams are now network independent. It's not anymore a single node that gets it, but the node can decide what information does it want to listen to and what information does it want to react to. And this kind of also gives a certain basic intelligence to the fabric that's independent of the nodes. You can just add a node, and it can just subscribe to various network streams and participate in it. This can be used to scale fabrics in a very dynamic way, for example. So this is a basic comparison of how this works. So unicast, you have one message going to one endpoint. Then you have broadcast. One message goes to everything. These two things are basic for Ethernet and for the standard networking, and nothing works without it. What is optional and often also disabled is multicast. So you have some nodes that want its information, others don't. And this is rather complex and often fraught with problems in terms of support, and it's usually a stepchild, right? Because everything can be done with unicast and broadcast. And then these guys like us, the finance industry, is at the long end, and that's like this LibFabric. So, and yeah. So the rationale for multicast and FSI, the basic thing is you want fast and scalable event notification. Because there's events happening at the stock market. The price of an entity changes. Everybody needs to know about this, and this could be hundreds, thousands of millions of systems. You can't do one-to-one transactions with all of those. So you want a fast notification of everybody, and they do that by inserting the information into a fabric or into a network of switches and routers, and the replication of the data is happening in these switches and routers, not by the endpoint. This is not only true for stock market events, but also for news. There's also news that affect values and stuff. And there's also other events that influence the valuation or things. So there's a lot of events that go on and event correlation that goes on in the financial industry in order to assess the value of a certain entity, a certain symbol, a certain marketable item. And so in order to, and one of the most important piece of information that's going to be replicated is the market data. This means a transaction was performed between a seller and a buyer, and now a new price was set for a certain product. And if that happens, everybody needs to know about this. And typically, if a price changes, there may be systems that want to take opportunities and want to kind of trade on this and exploit the change of the price changed. And therefore, they must react fast because there will be more trades going on later, and the value of the symbol may change again. So there is a very high pressure on low latency and fast reaction times to these event changes. So the event propagation must be fast, the processing of the events must be fast, and the reaction to these events must be fast. There has been a race going on like that for the last 20 years. And first it was in milliseconds, and it was in microseconds. Now we are in nanoseconds, and it gets worse and worse. Now they try to make the line straighter, the cable straighter. This is sometimes you think it's bizarre, but it gives you an advantage. If you would do this with unicast, you couldn't even do this because the capacity of these lines wouldn't be sufficient. This is the only way to do this is by a kind of have the application at the endpoints and write the switches. Also, usually the regular congestion protocols are endpoint to endpoint, so all these things don't work anymore. With multicast, you will have different congestion protocols and different ways of dealing with the fact that you send to multiple endpoints, and then it becomes extremely complex on how you make sure that everybody gets it. And there's various standards on this one that we're going to talk about later. And it's also traditional. FSI has been using multicast for decades, since the invention of Unix in the 70s. We've been doing that, and it's actually brewed into the Unix POSIX standard. The socket API that all Unixes use has extensions to support multicast because the financial industry was one of the first users of this. So there are special provisions for multicast use and multicast conventions in the early BSD stack, and they also carried forward over decades, and they're part of the standard Linux stack, for example, today, and they're supported by all operating systems. You usually don't notice these things, but if you look at the crannies, you see they're here and there are the bits that makes this possible. And also, it's also in the basic design of all routers and switches. High-end switches always support this. Low-end switches may not actually support multicast. For example, if you have a switch that you use in your home, the cheap one from Fry's doesn't support this. If you buy a Cisco switch, it will do all of these things because
That's the domain flooding.
It does what, domain?
Domain flooding. It's called bridge domain flooding. It means the multicast defaults to broadcast behavior.
Yeah, but that's not.
You guys call it.
Yes, okay. If multicast defaults to broadcast, then we don't have multicast anymore. All right. So the typical financial industry data flow. Just hopefully that also explains how Eurex works. You have a stock exchange. The stock exchange has a matching engine. In the matching engine, you match, sell, and buy orders. Right? So there's a kind of a business entity that sends an order into the front-end processor. I want to buy something. So it says, okay, I want to buy at this price. And another trader may send an order and okay, I'm going to sell at this price. And so the matching engine figures out what are the buyers and sellers, and if it has a match, then it sends, and then it makes a deal between those, and the value is transferred between the trader and the business entity, and the matching engine then sends all market data to all market participants. This has occurred, and therefore we have a new price. So then the data is replicated to all the various business entities, and everybody gets notified of this thing. They may react to that and send a new order to the front-end processor, which then gets sent to the matching engine, and it tries to do that again. And this is going on all day. And this cycle, market data to business entity to order, this has to be as fast as possible if you want to compete. If you hold on to that data for too long, it's going to be stale, and you may be reacting to a market situation that's no longer valid, and you actually may be losing money because the valuation is not as you expected it to be. So there are different areas in financial services, and they have different criteria for what they want from multicast and how they will use that technology. We've heard from Eurex, and so it's a stock exchange. So the main criteria here is fairness of access in addition to the low latency. This means all market participants must have an equal chance to get to buy the symbol and buy at a certain price. If that's not realized, then they will complain to the regulatory bodies, and as you've heard, there's often intensive investigations on why was a certain order executed a few milliseconds or a few microseconds late. Right, so that's why they have logs and all the other things. So a stock exchange must have reliability. You can't have the stock exchanges go down, which causes usually a major crisis, and it must be able to deal with the capacities and to have the bandwidth to also deal with major things like a sell-off. If you have a major crisis, usually the stock markets react in violent ways, and at that point, the capacities of these networks are stressed. So typically, you have a network use of less than 5% on an average day. If something really happens, this spikes in a tremendous way, and all components get overloaded. So there is issues with robustness as well as reliability and capacity here. Also, one of the reasons to use InfiniBand is because you have this high capacity. Then there's the banks. The banks mostly want reliability. Same thing with investment funds. Then there's algorithmic trading companies like us. We don't really care about reliability. We just want to win trades. So our infrastructure is optimized to be as fast as possible, and we sacrifice the fairness of access, reliability, and all the other things. We need capacity in case a major sell-off happens, and overall we need latency, because we need to have an advantage over the rest of the market participants so that we can get a deal if it comes visible. So various financial areas have different trade-offs, and will use different software and different criteria to get to this stuff. And so the multicast way they may use multicast also differs. With Eurex, you saw they have actually using multicast for failover between various matching engines, so that I can always have one that is active. So particular use cases when interacting with the stock exchange, there's a market data thing. So market data is widely distributed from the stock exchange, processed, logic applied to it, which results in seller buy orders. And then actually you do unicast transactions with the exchange. If you want to buy or sell a symbol, then you actually talk to just your gateway, and then you get unicast at a bay confirming that you have bought this thing. But on the other end, the market data comes out to announce to the world, okay, this price change has happened. So now, how does this multicast work in an RDMA fabric? So some of the characteristics of multicast traffic. Typically, the messages are very short. And one reason is because you want to be able to process it in a fast way. You don't want to have a complex structure in there. And shorter messages transfers faster because you need to serialize the message and put it on a wire. And the shorter the message is, the faster you can transfer it across various pathways, and thus you have faster communications. So typically, multicast must use an unconnected mode. There's no way that you have a connected mode with numerous endpoints. So this is always UD datagrams in terms of InfiniBand. And they're typically confined to the same subnet or partition of the fabric. That is true for hosts that are within the InfiniBand fabric. But on the other hand, the data often has to cross over to Ethernet to go to market participants that can only be reached via Ethernet. So there's often the need for gateways that transparently bridge the traffic into the Ethernet world, and also vice versa. So, and then this traffic, since it is one-to-many, there's no one-sided transaction here. The true RDMA transactions, where you write into the memory of a remote node, is only possible with unicast. So the true RDMA doesn't even work with multicast because this is just not possible. The multicast uses messaging through the RDMA APIs. So we don't directly write into the remote memory. We use the RDMA API to create a regular message, and that message then is replicated to the various nodes. So it's kind of, we're using it halfway. So the financial services require reliability, and that is where we have a surprising good feature of the InfiniBand fabrics, because they are lossless. And so even if you have an unconnected, the UD datagram, unreliable even, it is actually true that it always is delivered to the endpoint. So we are using the UD diagrams actually with a guarantee kind of, and expecting that they always arrive at the endpoint. So it is possible to have reliable data transmission through header facilities on InfiniBand, which is different from Ethernet. Ethernet always can drop these things on switches, on routers, and InfiniBand does make sure that the stuff arrives at the endpoint. So on the side, you see this RFC 3208. This is the typical process used for Ethernet in the financial industry to guarantee multicast packet delivery. Because packets can be dropped, the RFC prescribes a sequence ID assigned to each packet. The endpoint verifies that you have an increasing number of the packets arriving, and if there's a gap, it will ask the sender, okay, I missed these, send it to me. So there's a recovery protocol there. And this is also implemented by the WebSphere LLM that the Eurex uses, and various other products that are on the market for reliable multicast distribution. And in the Ethernet world, this is pretty deadly, because let's say a router consistently fails, and so all the lower level nodes may not get it. And you may have the situation now that 500 nodes ask for a retransmission of data. That's the packet storm, and it usually brings down the network. That doesn't happen in InfiniBand because you have reliable data transmission. So this was a big win for us, because we got rid of all the packet storms that we have seen before on Ethernet. So if you want to get more into detail on these packet recovery and stuff like that, look at the RFC. This gives you a lot of insight into the congestion protocols, collision avoidance, recovery, and avoidance of packet storms that have been used in the industry. There are situations in which even InfiniBand can lose packets if you don't service your endpoint fast enough. So in some situations, even the WebSphere does want a recovery. And some future on the wish list, what we like to see, what we haven't had yet. We want to have timestamps on receive and send. Eurex has a problem of finding out when did the packet arrive at which system. And you're smiling now, yeah. We all want this. And it seems that we have some issues there with the standard of the API and stuff that has to be solved before we can get that in. Next thing is multicast loopback prevention. When you send out a datagram, it usually echoes back directly to the host where it's coming from. So you need to process the useless data that's coming back to you immediately, which causes additional latency, and we don't want that. That has been, I think that's almost upstream now, and we're probably going to have that soon. Then packet aggregation. We often receive a huge amount of datagrams. And right now, you have a completion entry for every one of these things. It would be great if you could just say, OK, I'm going to accept 100 packets, and I don't want to see all the details on the 100 completion entries. Then offloads for checksums and segmentation. If I can automatically receive a datagram and can already segment it into the header portion and the payload portion, then I don't have to move the data around after I received it. That would be very good. One of the problems that has continuously plagued us is most of the things that we do on IB is based on IP over IB. Now you have two levels of multicast subscription mechanisms. One at the IB layer, that's native IB, and one at the IP layer, which is mostly IGMP, PIM spas, and all the other stuff. And those two things have to harmonize with the gateways that bridge the stuff to Ethernet. And this has caused a huge amount of harm and problems to debug and to troubleshoot, and we still had failures a couple of months ago with one of these things. So we really wish this would be something that would be cleaner and better. Enhanced reliability. maybe there's something we can do about not overrunning the QP buffers. Yeah, we'd like to have the complexity of the bridging reduced between InfiniBand and Ethernet. And we want more advanced multicast routing and failover when traversing the bridges to Ethernet. And what also would be good is some kind of a multicast traffic load balancing. As was mentioned by Eurex, the InfiniBand, the multicast trees are static. So there are certain nodes associated with an InfiniBand group, and the traffic of a certain multicast group always traverses to a certain core node, spine nodes, and comes back in a certain way. So if you have too much traffic on a certain multicast group, it's just congests your fabric. It doesn't go to the next spine node. And so something like adaptable, dynamic, routable multicast traffic would be very useful, so that we can use the entire fabric for routing multicast traffic and not just a single path through the fabric. And then one of the issues that always plagues us is this slow consumer problem. What is good about InfiniBand is that it doesn't drop packets. It guarantees the delivery to the endpoint. What happens if one of the endpoints doesn't consume it fast enough is it slows down the sender. This means everyone gets traffic later, which is very bad in finance, because we do these things because we want low latency. We don't want the sender to be stopped. So we have some hacky solutions right now where we just disable the losslessness of the fabric at the edges, but we really wish there would be some standardized way to do that, so that the endpoint can tell the fabric, okay, I'm going to receive this, but don't bother slowing down the sender if we can't keep up. And on the side, here's the IGMP quotation. If you want more detail, this is the basic protocol that governs our multicast subscription on the IP layer, which has to cooperate in a nice way with the InfiniBand protocol. And that was all my complaints, and I'm pretty much done. So if you want to know anything else, just ask, and I can expand on that. But whatever you want to know.
I have a question. So how this product differentiates between like 29 West and TIBCO solutions? So we can hear you. There are companies like 29 West, TIBCO, they have all these reliable multicast solutions. Even IBM has some. So how that is differentiated from the competitors?
Well, most of these.
Can you repeat the question?
Like the question was, there's various middleware vendors like 29 West, TIBCO, and WebSphere, LLM. How are they differentiating themselves? Most of them implement a variety of RFC 3208. If you read that, you basically have most of the internal workings of how their middleware actually works. The details on how they interpret the standard and how they actually realize congestion control, elimination of packet storms varies from vendor to vendor. So they are constantly evolving, and they're competing with one another, trying to better the packet storm detection and all the other things. So, yeah. Yeah, that's the things that change, but my company has decided that all this middleware is in the middle and it's bad, so don't use it. Because if something's in the middle, it causes more latency. So, since you have direct ability to use the losslessness of the IB fabric, why do we need this? Any other questions?
Have you been able to employ any strategies in routing to avoid any of the congestion you have in multicast, or are you kind of stuck with the technology it is today?
We have various talks with a vendor about how to improve the situation, but so far this hasn't resulted in anything. I think we have maybe in 3 months, hopefully we'll have something.
Okay, thanks, Christoph.